The larger the mass of an object, the larger is the force needed to change the direction or its speed. Think of trying to push a car compared with a bicycle. Also, the faster you want something to get moving, the bigger the force needed. Think of pedaling a bike. The harder you push, the quicker you get going. The relationship between force, mass, and acceleration is known as Newton's second law of motion. It can be summarized in this equation. Resultant force equals mass times acceleration. When force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second.
Newton's second law states that the rate of change of momentum of an object is proportional to the applied force and takes place in the direction in which the force acts. Force acts on an object of mass, m, and its velocity changes from u to v in time, t. By adding constant k, this equation can be obtained from the relationship F, directly proportional to m, a. The unit of force is Newton, and a force of 1 Newton is defined as the force that can produce an acceleration of 1 meter per second when it acts on an object of mass 1 kilogram. This equation gives the mathematical form of Newton's second law of motion. Note that F in the equation, F equal to ma, refers to the resultant force that acts on the object. Newton's second law of motion describes the relationship between the acceleration of an object and the force applied to it. Acceleration of an object is proportional to the force applied. This means that acceleration doubles when the force doubles, or acceleration trebles when the force trebles. Thus, the greater the force, the greater the acceleration. This graphical relationship is represented as shown. If the force constant and double the mass, the acceleration will have. This means the acceleration is inversely proportional to the mass. The greater the mass, the less the acceleration. This graphical relationship is represented as shown.
A spacecraft with a mass of 7,150 kilograms accelerated away from the International Space Station towards its re-entry point with an acceleration of 2 meters per second relative to the International Space Station. Calculate the resultant force on the spacecraft. Pause the video and work it out. How about this example? A car of a mass of 1,200 kilograms starts moving and accelerates on a racetrack. The car's engine produces a constant force of 3,400 newtons. A constant frictional force of 400 newtons acts on the car. Calculate the acceleration of the car. Pause the video while you work it out. Now calculate the force required to make an 800-gram toy car accelerate at 8.2 meters per second. Take care with the units. And the mass of an object accelerating at 0.8 meters per second when a resultant force of 200 newtons acts upon it. So why do you think you can throw a tennis ball much faster than a shot put? Because the force from your arm is the same, but the mass of the shot is much bigger, so its acceleration will be smaller.